Good morning, good morning. Welcome, welcome. Very happy to see all of you here today. My name is David Corliss. I'm from General Motors in their auto insurance group, OnStar Auto Insurance. Today we're going to be talking about bias in machine learning. We think we've heard about problems with bias. The approach to today's talk is look at the root causes of bias. We're going to look at how we can, in the development process, instead of after the horse gets out of the barn closing the door, in the development process, designing against bias in machine learning and AI, and make it a regular part of the process. So we're going to talk about root sources. We're going to talk about a process to design against bias, instead of responding to bias or not responding to bias, which would be even worse. Instead, we're going to be talking about how, from the initial conception of a project, designing against bias in machine learning and AI. A little bit of information on myself. I've been working in the data for good space for a number of years. There's a talk in the next session after lunch on data for good. Folks from Oakland University, I know some of those folks. I've been working in that space for a number of years now. Write an article for the American Statistical Association, a column in their monthly newsletter, getting involved in data for good. You can find us there at Stats for Good at AMSAT News. So, what is the problem here? I mean, wasn't the idea that we were going to use machine learning, we were going to use artificial intelligence? I don't know if that's the best description of it, but it's one everyone remembers. Wasn't the idea that we were going to have these computer algorithms and have them replace human decisions, and that was going to make things better? Wasn't that the original idea? That often hasn't worked out very well, has it? So what went wrong? We're going to look at root causes of bias, and understanding that better, we're going to be looking at how to design against bias in the design and development phases of machine learning and AI projects. Give you a couple of examples. Racial bias. So in this case, the so-called solution, the machine learning algorithm is going to decide who gets bail, who gets parole. In particular, it's a predictive algorithm. Come on, folks, we've seen a lot of predictive algorithms. This one predicts recidivism. What's the chance that if you let this person out on the street, will they commit another crime? And the idea was that in the past, certain judges, have been particularly hard on certain people, especially certain groups of people, AKA young black men, some other groups, Native Americans. You don't hear about that as much, but you look at court cases in the area where there's a high Native American population, it's a major problem. And there are other concerns about bias in the judges, in the parole boards. Let's come up with an algorithm and it's supposed to solve the problem, right? Well, here's the algorithm. This is Compass algorithm. It's a proprietary product. It's one of the things that's used in several states. It has serious problems, but it is still used in several states. So here's the problem. What we've got here is this machine learning algorithm, which was supposed to remove racial bias. The algorithm is biased. It creates the exact same bias that it was supposed to eliminate. Now, we can have a look at that, and we can see some of the things. We're going to look into that in a little bit more detail, but there are two things that really jump out at us as we look at this slide. One is we don't really know how it works. It's a black box algorithm. We know the factors that go into it, but we don't know what weight they get. And so in this case, especially for an algorithm that's functioning in the public square, now we're not looking at an algorithm here where we're predicting who gets a mortgage or something like that. We're not doing an algorithm where racial bias isn't going to be a concern because you're looking at parts coming off an assembly line. In this case, we're looking at people in the public sector, in the public square. And so a black box algorithm simply doesn't belong in this space. We need to know how it works. We need to have accountability on it. Also, let's look at the individual factors. You find out that individual factors have racial bias. Just to give one example, age at first arrest. The younger you were when you got arrested for the first line is supposed to be a predictor of recidivism. But let's look at some 14-year-old who gets into a little bit of trouble. Did that person get a talking to? Do they call the cops? Is there racial bias in what that age is, whether or not the person gets arrested or simply sent to the principal's office or scolded, set straight? An actual arrest that gets recorded. You see how there's bias in the data. And so when we put in biased data, we're going to get bias out. Here's another example. This one was detected by investigative reporting, reported in Reuters, which is a European economics and business magazine. Amazon, of all people, let's not get down on Amazon, let me tell you. Amazon did one of the coolest things that you will hear about in this space. First, we have to set what the problem is, and then we'll talk about how they address the problem. But the idea was, now, folks, we got a lot of really smart analytics people here. I'm going to tell you a little bit of story about the concept of the Amazon algorithm, and some of the people who are more on the business side or HR side might think, oh, wouldn't that be great? But if something is too good to be true, it probably is. This is an example. The idea was, you see, Amazon was seriously concerned. This is one thing Amazon did right. They were seriously concerned that women weren't getting hired, weren't getting promoted. It's a problem in tech. It's a problem in a lot of areas. So what do? Well, we're going to write an algorithm that's going to read resumes for us. It's going to screen the algorithms. We're going to hire the top 5% of resumes, let everybody else go, and the whole problem goes away, as if AI were magic. So just the concept. Now, what this tells us, though, seriously, is there was a disconnect between really, 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 really talented people at Amazon. Amazon would write a better algorithm, but there was a disconnect in concept between the algorithm writers, between the tech people and the business people. And the tech people had outsized expectations of what AI could deliver. Now that's something that we have to be on the front line to fight against. When we talk about designing against bias, we have to make sure that the people who are going to be the consumers of our products don't have an inappropriate idea of what we can do. We're not going to say, hire the top 5% or give a loan to the top 5% or give parole to the top 5% or something like that. And then problem solved, there's going to need to be a little bit more done and some follow-up on this as well. So it actually starts with a business expectation problem, not a technical problem, where business didn't have an appropriate expectation of what to think that they were going to get delivered by the tech. So what went into the resume? What was in the algorithm? We'll talk more about that in detail. This is a classic example of not one but two different kinds of problems. And it ends up with when they screen the resumes, it had the exact same bias they had to begin with. To Amazon's credit, they detected this problem and never deployed the algorithm. They actually checked. This is not what happened with the Compass algorithm. It was put into use. It is still in use in many states. The Compass algorithm is doing a great deal of harm. In this particular case, Amazon tried to eliminate, I don't know if you can completely eliminate, but at least tried to address bias using an algorithm. The algorithm failed, and so they decided not to deploy it. Kudos for Amazon. But the algorithm could have been designed better. We'll talk about how that happened and how you can, in the design phase, prevent this kind of problem from happening. This is a separate problem from the previous one. So let's look at how some of these biases get into our machine learning and AI. Here's an example. We're talking about an algorithm that's trained using a bias subset. Now this one should hit close to home because this happened right here in Detroit. We've got Najibi out of Harvard. He's looking at facial recognition software. He compared a number of different, very prominent, very well-known companies doing facial recognition, and guess what? It's not very good at identifying women or people with darker skin, people that might represent a smaller subset of the population, Let me ask you, no, not all of you. Let me just ask the women in the audience, if I may. How many of you have trouble getting voice recognition to recognize your voice? It's a common problem that women are less often understood by AI because they're more often trained on either male voices, or the AI is trained on male voices or principally on male voices. In this particular case, we've got a particular subset of the population that was a smaller subset, and a particular subset that we're very, very concerned about being adversely affected by use of this algorithm. We'll talk about the application in a moment, why it's a big deal. We should have been concerned about one particular subset, and yet they were undersampled. So oversample, folks, if there's some small subset, this is just like, we wouldn't have to do this for AI, you do this for a plain old logistic regression model. You're gonna oversample cases that you're particularly concerned about. If you're looking for fraud, that's unbalanced data. I don't know if you call 12% of the population unbalanced, but it's certainly not. If you're gonna train something that works best on just whoever walks in the door, or some general subset of the population, you're going to find that you get an algorithm that doesn't work very well for small groups, sometimes important groups. So what was the result of that? This was in Detroit, folks. There's a project called Project Greenlight, and it put up cameras at stoplights, and it would photograph people. And the idea was to try to catch people who would be running stoplights and so on. But in this particular case, we find places where the data were collected, where the cameras were. We look at where they put the cameras in the city of Detroit, I should say generally the Detroit area, and we look at the Census Bureau demographics, and darn if that's not a match. And so they're oversampling, they're putting extra policing in areas where there are more black folks and fewer cameras photographing people at stoplights in mostly white neighborhoods. This is a problem. And so what you get is, when you have a biased training population, you have biased results. If you undersample small groups that you really care about, if you apply this with racial guidelines in the application, these are things to avoid in the design phase. Before you even write a single line of code, we're talking about data collection here. If you bias the training population, you know that the results are going to have bias in the algorithm. Root cause of bias, here's another one. I'm going to call this the history problem. Now, if you look this up in scientific literature, you're going to see a different name. I think this is a better name, but just a caution, some people will call this prejudice. No, very often called prejudice bias. And if you look at bias against women, or bias against persons of color, or bias against LGBTQ+, or any marginalized group, there are times when there really is prejudice, and there's a concern about that. The type of problem doesn't only exist in prejudice, it's found in other places too. And so I don't like using the term prejudice bias. You look it up in the journals and stuff, that's what you'll see. I'm going to call it by a different name. I'm going to call it history bias. It better describes the problem, and there are sometimes, again, you can have the same kind of problem when you're dealing with parts coming off an assembly line and there aren't any marginalized populations you need to defend. The history problem. The idea, machine learning is going to replace human decision making. So we've got, some Keras TensorFlow algorithm here. So, in the old days, we had human beings looking at resumes and screening them. We use a resume screening example. And we're going to replace that with an algorithm instead. But here's the problem, and it's a design problem. The problem is that you're going to train the algorithms on previous decisions, historical. That's why this is called the historical problem. When you train the algorithm on previous biased decisions, the only thing you're doing is training the algorithm to do the exact same bias that people already had. This is a very real problem, bias in, bias out. When your training set consists of records that were human selected with human bias, You're just telling the machine to recreate the exact same bias people have, and the bias will remain in your system. You have to be very, very careful of the training set. It can't be previous human decisions. And it isn't just, men and women and demographic subgroups. Consider this. How about an algorithm that detects parts coming off an assembly line? And you want to improve the process. We always want to get, better detection of parts with defects, right? So we're going to train the algorithm based on the parts that we found before, and the algorithm is no smarter than the human QA inspectors because it's simply trained to do what they did. It may do it faster, lower cost, works 24 hours a day and doesn't get tired, but if we train it on the previous human decisions, the historical data, you have to be careful about the data you select for the training algorithm. That's a design question. Here's another one. I'm going to call this the spaghetti problem. Oh, actually, I'm going to back up for just a second. Algorithm trained on previous human decisions. Remember the compass algorithm? Who gets bail, who gets parole? Classic example of this. Classic example where previous biased human decisions, the decisions from previous judges that had bias, and we're trying to fix that, but those decisions became the training data set. They weren't independently reviewed, and so the algorithm had the exact same bias that people did because that's exactly what it was trained to do. Spaghetti problem. Lots of predictors. I make a little bit of a joke. See, once upon a time, there were these things called libraries, and they had whole buildings full of books. And somewhere in that library, you would find a dictionary that looked like this. I've got one at home. It's from 1903. It's something of a museum piece. But if your data dictionary looks like this, if you've got hundreds, thousands, tens of thousands of predictors, this is a very real possibility, especially when we get into natural language processing, or if you're in a healthcare situation. See some people nodding their heads. That's good. In healthcare, if you're looking for genes, you know how many genes there are in the human body? You're talking about something that could run into the tens of thousands, routinely 40,000, 50,000, sometimes up to 100,000 different possibilities. And so it isn't only text, but text offers some really good examples of it. When you have many, 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 many candidate predictors, and then you take anything that sticks, there's this old wives' tale that if you take spaghetti and cook it, it's done when you throw it out the wall and it sticks. Actually, I'm told from spaghetti experts like my wife and her entire family, it's probably overdone at that point, but that doesn't matter. We've heard the phrase, if it sticks to a wall, it's done. So here we're going to use anything that sticks. We're going to look through thousands of potential predictors. We're going to come up with hundreds of whether it's natural language processing or individuals who are making assessments or students in a school or what have you. When in a school district, there are thousands of possible predictors, and we're going to uncritically accept anything that comes out of the feature importance analysis. This is especially a problem with natural language processing. It shows up in other areas. When the algorithm is trained on anything that sticks, anything that looks predictive, without looking to see if there's bias in those individual predictors, bias predictors, bias outcome. Yes, it's a lot of work because there are a lot of predictors in some of our models. But we have to individually screen those predictors for potential sources of bias. We'll talk about how to do that in a minute. So, how do you measure bias? Can bias actually be measured? Well, it turns out that there are some folks that have been doing this for years and years and years and years. They use something called disparate impact. It's people who work in social workers, people who work in public health. This is something that all of us have heard about all our lives. This is just the measurement technique. We're only talking about how you measure bias. And we're going to, this problem disproportionately affects black folks, women, immigrants, go down the list, whatever particular group, young folks, people in poverty. There's a disproportionate impact. This is how we're going to measure bias. Now, this isn't a bias situation. This is a public health study, one that I did a while back on the COVID pandemic, Might have presented that here a couple of years ago. But I know I gave some talk on COVID here in 2021 when we were virtual. So this might have been a part of that. But here we're looking at, we take all the counties in the United States. We divide them into quintiles. We divide them into 5 groups. So all the groups are the same size. 3,200 counties, 640 in each bin, roughly. And we're taking by the percentage of persons of color, BIPOC, I should say, Black, Indigenous, persons of color. We look at the percentage in each county. We use Census Bureau demographics. And so what we look at, this is in the very first wave, just a little quick FYI, very first wave of the COVID pandemic, before politics got involved. I'm not going to talk politics, this is before that. We're talking about March, April, May, beginning of June of 2020. So very early in the pandemic, before we knew what was going on, before politics got involved, before we had treatments or even effective means for detecting the problem other than clinical. A doctor looks at you and said, yeah, it looks like COVID to me. What we find is that in the initial wave of the virus, what this gets at is pre-existing conditions. You talk about pre-existing conditions. And so what we find is that mortality, which is more likely to get reported than simply getting sick, sometimes that gets missed. We find disparate impact. This is just a public health study. This is a garden variety kind of thing. But notice how we've looked at a particular group that we're concerned about. We've taken in this case, places in the US with the least, in the middle, with higher, and then the highest. And we see that in this particular case, the adverse outcome. The adverse outcome could be denied for a loan, or whether or not you get parole, or whether or not you screen and the algorithm, the person gets an interview, or gets denied an interview, or denied promotion. Whatever the particular adverse outcome is, we see that the adverse outcome increases in likelihood with the increase in the percentage of some particular group we're concerned about. This has been around for a century, folks. People have been doing this for a really long time. But the method is how we can measure the amount of bias in an algorithm. We're going to measure it the exact same way. We're going to measure it with disparate impact. So here's the follow-up. Here's what the chart looks like. Again, this is not an algorithm. This is, does COVID hurt some people more than most? And we're looking at pre-existing conditions, and it's no surprise that having chronic lung disease is a pre-existing condition that impacts mortality from COVID-19. And so the pre-existing condition most likely to kill you is being Black, just slightly ahead of being a cardiac patient. This is how we're going to measure whether or not bias is present. This is not an algorithm at all. We're going to use this tried and true measurement technique that's been around for a century. This is how we're going to measure the impact. So what do we do about it? One of the things we do, I'm going to call this a bias minimized comparison algorithm. What we're going to do, we're going to develop our model, but we're also going to develop a short model. By a short model, I mean it's going to have a fewer number of fields in it. We look at all the stuff that looks predictive. We're going to build a second model with only stuff that we have tested. How did we test it? That's how we tested it. We're only going to look at predictors that don't show signs of bias, show very little, if any, within the range of uncertainty. We're going to have an algorithm, that statistical model, an AI. We're going to have fewer predictors, only those that we're really confident have absolutely minimized bias. Notice this is bias 0 is bias minimized, that's the end in BMCA. We're going to write a second predictive algorithm. It's not going to perform as well. We all know that when we take some features out of an algorithm, it's not going to do as well. But we're going to focus on only those that are free of bias, and then we can compare the two results. We can compare the two, the algorithm we'd like to use, and this other algorithm over here, which doesn't perform quite as well, but is bias minimized, and we can use it to measure the amount of bias. And so we can tune the bias in our production algorithm by comparing it to this bias minimized algorithm, and we're going to measure it using odds ratios. These are odds ratios. For example, the guys to the top line here are 10.1 times more likely to die than the average of the population. Whereas high population density city centers, 1.9 times as likely to die than the average of the population. So these are odds ratio. They tell you the likelihood of the bad outcome happening, and this is different from the population as a whole. We're going to compare it using these odds ratios. And that's how we're going to be able to tweak the algorithm and reduce the amount of bias present. Some new tools have recently come out that have made this much, much, much simpler. A prominent one is the Fairlearn algorithm. It was produced by a team at Microsoft, but it has been open sourced. It's in Python. I'm currently writing a version in SAS. I haven't seen anything good in R just yet, but it can't be that long. But most of us who are doing analytics, or at least have somebody on the team who can do Python, and this is available now. It was open sourced, I think, November of last year, so it's pretty recent. If you're worried about bias, get the Fairlearn algorithm. If you don't program Python, learn Python, guys. But if you don't program in Python, get somebody on your team that doesn't have them use this. Get the Fairlearn algorithm, developed by a team at Microsoft. It's been open sourced. Get a hold of this. Now, what we've got here is a confusion matrix that is the ones you got right, the ones you got wrong, both the yeses and the nos. That's how you get the 2 by 2 here. And then we've got it broken down by, notice on the left, not African American in this example. It could be men and women. It could be old versus young. It could be this city versus that city. It could be different things. In this case, it happens to be race. So this is, in fact, an analysis of the COMPASS algorithm, which we said had problems with it. You know, it doesn't help very much to go into court and say, hey, your algorithm's all screwed up. Look what's happening. It's nice when you can have the numbers that measure the amount of bias and measure the impacts. It's good to be able to quantify it and not just say, we think there's a problem here. So in this particular case, we've got on the left, not African American. In the center, we have African American. And on the right, we've got the difference between the two. This is a graphic that's produced by the Fairlearn algorithm. If there's some other code you'd like to use, let's try to recreate this functionality. It's been open sourced. Let's see if we can get this kind of technology to more people. You look at the people that, you know, the general population or a favored group compared to a sometimes disfavored group. Remember when we were looking at screening resumes, it would be men on the left, women in the middle, and the difference. The cool thing about Fairlearn is two things. It shows you the difference, and if there's a big difference between the groups, that detects bias. The other thing Fairlearn can do is you can have multiple versions of a program. Remember I talked about how this bias minimized algorithm? Yeah, I see someone taking a picture of this. If you're going to take a picture of one slide, make it this one and the next one. So this is what Fairlearn outputs. You have different versions of, maybe you're going to try different predictors. How do you measure if there's bias in a predictor? This is one way to do it. Here, each dot is a different version of the algorithm, slightly varied. Maybe it's a different training data set. You're worried about bias in the training set. Maybe it's different predictors, whatever it is. In this case, we've got like 18 different versions of the algorithm. Further to the right is more accurate. Further to the bottom is less bias. And so in this particular case, you can see one very, very nearly at the bottom, just at the right of 0.75 in terms of accuracy. It's not the most accurate, but it's not far off, and it minimizes the bias. So you can try multiple versions of your algorithm and minimize the bias using the Fairlearn algorithm and still get good performance. You're going to have that trade-off. It's often a struggle to balance between the power, the accuracy of the algorithm, and eliminating bias. This allows the business to make a well-informed decision as to which version of the model is best to use. I said we're going to take two pictures of slides, the previous one and this one. But to sum up, good things to do. Parsimonious models. If possible, don't throw 100 different things or 500 different things. Sometimes you're going to do something like that, especially when you're looking at natural language processing. But when you get lots and lots and lots of predictors, you can run into problems. Parsimonious models as much as possible. Greenwald predicted for bias. Remember the Amazon resume screening algorithm? Turns out, according to the report in Reuters, you lost points in the algorithm if it looked at your resume and picked up the word softball. Now, how many men play softball in college? How many women play softball in college? These are the kinds of uncritically accepting any predictors. This is the classic example of the spaghetti problem. The algorithm from Amazon had two problems. One, it was trained on previous human decisions were biased. Two, it didn't look at the individual predictors that went into the algorithm, and there were a lot, but no one went through and said, we're trying to prevent bias against women. Is age biased against women? No, there's women of every age. Okay, and then go down the list. You know, and was it like the word softball is in the resume? I'm sorry, but that's got a difference between men and women in it, doesn't it? So that's not a predictor we're going to use in the algorithm. You got to screen individual predictors. Make it part of the process. Nobody would put code into production without doing a code review. Nobody would use data that hadn't been screened to see if the data had lots of missing data or corrupt data and things like that. We all know the process for writing algorithms. Testing for bias needs to be part of that process. I'm going to say that again. This is the takeaway. This is the bumper sticker. Testing for bias is possible. Testing for bias needs to be a regular part of the algorithm development process. Use transparent methods, not black box. I think most of us are aware of that. Develop a model using the outcome screen for bias. Remember the history problem. In this case, we're screening outcome for bias. The spaghetti problem, we're screening the predictors for bias. Bias in, bias out. We have to screen both the predictors to see if they have bias. We have to screen the outcomes to see if the previous decisions that we're using to feed in are really the outcomes we want. Maybe we need to go through the individual outcomes and one by one, check them out and say, was there a problem here with this particular outcome? This would have helped the Compass algorithm. Use odds ratios, that mathematical method. If you're not a stats type person, talk to somebody else about it. But odds ratios, this is used in public health studies since the dawn of public health studies. Use odds ratios to measure the impact. And wherever possible, open source the data and algorithm. Now let me talk a little bit about open source for a minute. If it's in the public sector, darn well better open source it. There's no excuse to do it any other way. How do you open source a proprietary algorithm? Well, you know, I work for General Motors. You've heard of us. It's a big company. How can we open source algorithms? We can bring in other people from General Motors, no, I'm not pointing over here, who can screen our algorithm and do an independent peer review inside the company. And if you can't do it, then you can bring in a contractor or a vendor. If you've only got 5 guys and you don't have another team over here, bring in an outside source, someone who has an NDA, someone who's going to screen it for bias, someone who can do an independent review. You can effectively open source it within the company, or if you're a tiny company, a lot of us are, you can bring in an outside vendor to do an independent review. Nobody would submit their books for the year to the IRS without having an auditor look at it. You can bring in an outside bias auditor. There are people who know how to do this. You might have one inside the company if you're a big company. If you don't have such a team, think about getting one, or finding some people that have worked in this space and use them to do an audit. You can open source the data in the public space. If it's proprietary, open source it within the company and do an audit for bias. References? Time for questions. Question? Yeah, so this might be a little bit into the weeds, but as you know... 10 minutes for questions. Shoot.
As you know, principal component analysis is used to pre-process data for machine
I'm going to use a slightly different word, but first let me start with what principal components is for folks who haven't seen it. Okay, so the idea of principal components is the idea of a statistical, the theoretical concept of developing a predictive model. There's something that I'm going to call the variability space. And what I mean is all the different reasons why some number can move the outcome. Let's look at, I'll just pull something, look at whether or not you get approved for a mortgage or not, pre-approved for a mortgage. That's a good one. Because it's not something I do, so it can't be speaking at all to anything I've worked with. Let's look at mortgages for just a minute. Well, income would be a good thing. And, you know, the value of the house, and is it overvalued, or is it likely to be, you know, severely underwater on day one? That's the thing, that all the different things that can predict whether or not you're going to pay off that loan. And they tell you different things. So what you want to do is find the best predictor for all the different kinds of variation, have a separate thing for each. What principal components does, it looks at this kind of problem. It looks at when the data you collect isn't necessarily a perfect predictor of what you actually want to know. Or you might have a number of things that all point in the same direction, like, again, go back to mortgages, income. Well, there's income, and then there's savings, and then there's side income, and how long have you worked at your job, and all of these other factors. And they generally point in one direction. Principal components is a statistical technique that can combine multiple factors into a simple arrangement and say, here's the point for here's the point for wealth. Here's the point for, you know, your credit rating, and are you in the habit of paying your bills? And some other things. Another one, is this individual house that you're buying a good investment? Is it likely to, you know, burn down, get vandalized, whatever? Is anything, or is it in a floodplain? Is something going to happen to the house that you're using as the collateral for the mortgage? Different kinds of variations. Principal components lines up the data you have with the answers you want. And because of that, I won't say it contributes to bias, it contributes to hiding bias. When you use principal components, it makes it harder to find the bias because the original data isn't there anymore. But you can take the new variables that are created by the PCA, the principal components analysis process, and you can test them for bias just like any other variable. So if properly handled, this complexity reduction technique called principal components, PCA, can make your algorithm stronger. You just have to be careful that you test for the new variables for bias just like you would have tested the original variables. Does that work? Great question, great question. Cool stuff. Question over here and then over here. Let me repeat the question. The question was, how do you identify which variables to test? Now, give an example, one that worked out well. Amazon was worried that women weren't getting promoted, weren't getting hired, that their resumes ended up at the bottom of the heap or in the circular file. So in that case, they were already aware of an ongoing problem. Generally speaking, we're worried about bias against marginalized groups. And so very often it's, if you simply look at diversity, equity, and inclusion, look at the kinds of people that we're concerned about, those are the variables you're going to want to look for. So we can look at where there's been a history in the past of a particular group. And even if there's absolutely no bias, which is great, it's good to have the numbers, isn't it? You know, we're working in, just to throw something out, we're working in North Dakota here. Lots of Native Americans. We haven't, some other group hasn't specifically looked at Native Americans, but we're going to look at Native Americans because it's a sizable proportion of the population. And we're going to include that as a special factor. You need to find the people that have a history of not getting a square deal. And part of that is being open to the people in your own organization and ask them, what should we be looking for? I think we understand that we should be looking for race. And almost always we need to be looking for gender. But age, we've heard about age being a problem. That's something that needs to be looked at. Especially good for decision trees, because we don't know what old and young is. I'm of a certain age myself where old people think I'm young and young people think I'm old. And so, so a decision tree is particularly good at making those decisions where the numbers break between one group and another. And you might need multiple decision trees. We might find that people who are very, very elderly are less likely, if you're 105, it might be hard to get a 30-year mortgage. And if you're 18, it might be hard to get a 30-year mortgage. So you might want to have multiple breaks in the data. Decision trees are a good way to do that. But talk to your people. Look at the groups that have, at times in the past, gotten the short end of the stick, and make sure you test for them. And even if there is if there's bias, you want to minimize it, of course. But more importantly, even if there's no bias, you've got documentation of it. You've tested it for it. You've looked for it. You've measured it scientifically. Here are the odds ratios. You know that this particular factor isn't a problem. It's not the greatest answer. Who to look for is like the people who've gotten hurt in the past. That's a little bit something of my own history problem, isn't it? Past outcomes. In this case, people who've gotten hurt in the past. But talk to your own people and ask them, what are the groups that you should be looking for? Great question. Great thought. I think Chris Smith here in front, and then in back.
So this is kind of about the human element. You talked about Amazon's problem with recruiting and how they wanted to make that change.
Yeah.
Do you have any thoughts or experience or takeaways for how to potentially convince others outside of the analytics organization that it's a problem worth fixing?
The question is, how do you convince people outside of analytics that we should do anything at all? Is it a problem worth fixing? I think that there is an increasing awareness that bias is a problem, but in particular, the people that I would talk to, the way I would approach that problem is identify champions. A lot of companies are already doing this. They're finding people there's a equity, diversity, and inclusion group or something like that. Identify executive champions. Designate this person as, for example, we've all got someone in charge of data governance, just as an example. There's someone in charge of data governance in our organization. In the same way, we can have someone in charge of algorithm integrity. And is the data good? Is it reproducible? Does it have bias? That's a host of things. It could even be a subcategory of data governance. This isn't what data governance is, analytics governance. But identify executive champions, people at a high level in your organization that are already eager and anxious to work on this, and make them the ambassadors for bias reduction across your organization. Great question. Question in the back. I didn't see who that was. Yeah. Mm-hmm. And so, great question. And so let me add something to that. In that particular case, we had a person from Ecorse, Michigan, a working class community that was part of the Green Light program, and now it's gone. But the legacy, the aftermath is still there. I use the example of COVID-19 just to show how to run the numbers on this. But I had occasion to write in my column for the American Statistical Association about the Tuskegee syphilis experiment, which caused a lot of distrust against vaccines and the medical community in general within the African American population. And frankly, I don't care what color your skin is. If the Tuskegee syphilis experiment doesn't keep you up awake at night now and then, there's a problem, okay? But I had occasion to write about Tuskegee during the pandemic, that it was a crime against humanity that's still killing people today because it had bred distrust. This is a question about that. Now that it's gone, how do you rebuild the distrust? I'm going to give an answer similar to this one. It's a little bit different. How do you get it within your organization? Appoint champions. Within a community, how you deal with bias, whether it's by neighborhoods or cities. We have an example there with the city of Ecorse, Michigan. Or it might be something that we're going to see in the future. For example, we're having a cohort of people who were remote schooled during the COVID pandemic, and are they going to be at a disadvantage going forward? That's a potentially marginalized group. Maybe when we talk about what variables to mention, hey, what grade were they in when they were homeschooled during COVID? Again, appoint champions, but these are community leaders. Maybe they're business leaders, maybe they're politicians, but usually not. This is not a political statement. I don't care what party you happen to be a part of. Most people don't trust politicians. So you want to have other kinds of community leaders. Maybe they're running a community center. Maybe they're running some religious organization. They're somebody who's respected in the community, and make them the champions for bias, not only for mitigating bias, but have them as a trusted source of information. So what I would suggest to the folks in the city of Ecorse is, who are the newspaper reporters for the local newspaper? Who are the people who are speaking at town halls? Can you get some of these community leaders to get the word out in the community through the Rotary Club, through the schools, through the religious organizations, whatever they happen to be? How can we use those champions as leaders in the community to get the word out? To say, one problem has been addressed, and here's the next problem on our list. Very, very much like you do inside, but now we're doing it as a community organizing activity to approach the community. Thank you very much. Are we out of time then? We're out of time for questions. Thank you very much. I am here all day.